Thank you. Well, good morning, Stuttgart. Very happy to be here at the Reliability Days conference. Okay, I'm Adam Barrett. I'm the owner of Apex Ridge Reliability. Apex Ridge is a reliability engineering consulting firm based in Boston, Massachusetts. And customers like Boeing, Google, Hyundai Motors hire myself to come and assist with building products and designing products that will always work, never fail for their customers. I do this in two ways. I do this by helping their engineering teams understand and implement reliability tools and methodologies. The second way I do this is working with their leadership to help them create a culture of reliability that ensures these tools are very effective and they get the maximum return on investment. And that's what I want to speak with you about today, is about the culture, a reliability culture. So let's talk about what is the definition of culture. We need to start with having clear definitions. This is very important for any kind of communication. There's a lot of definitions for culture. But in this context, culture is the environment that we're operating in. It's the feelings, it's the rules, it's the people. I used to say that culture, the reliability culture, was the foundation that Design for Reliability was built on. But I don't think that's an accurate description, because the foundation is just a start. It's the environment. It's what continually nurtures or can actually digress something, or it could shape how it works. So it's the environment. We need to think of it as the environment. So what is reliability? There's a lot of definitions. In a lot of ways it's implemented. I believe one of the best definitions is that reliability are the tools that allow us to make an invention mature. Because inventions and technology have really little value to us until they're mature. They can't deliver what they've created. An example of this is a DC motor that I built with my 10-year-old daughter for her class. They were doing projects on electromagnetism. And this motor, if I can get this to, this motor, although it does work, really has almost no value. This was first done, this type of motor, about 180 years ago. It's kind of cool, right? You see electricity turning into physical motion. Now, you couldn't put a fan blade on that. It wouldn't work. It has no use or no application. It wasn't until it was matured into a full product that now you can't imagine our lives without electric motors. They're in everything we do. So it wasn't until it became matured through reliability process, formal or informal, that it became valuable and we were able to use the technology. So, without a good culture for reliability, Design for Reliability tools that are very powerful have limited impact. So I wanted to talk a little bit about the experiences that I've had and observed, and I know you have as well. I'm sure I'll see a lot of nodding heads of Design for Reliability tools not being able to yield their maximum value. So some of the common tools that we're very used to using are halt testing, stress margin, reliability growth, accelerated life testing, used in the product development process. So how do they fall short in giving the maximum benefit to the program? Let's take a look at halt testing. Ideally, halt testing should be used at multiple points in the program. We should be using it when we're first creating a technology, even as just a simple subassembly. We should be using it as we're incorporating previous technology. We should be at the point of prototype doing halt testing. And we should be validating at the end the final version and changes from that design input. Now, typically what happens, as we know, is you end up getting to do halt testing once. Right? It's not until there are some prototypes, maybe even after the prototypes, because they were used for functionality testing, that you get to do the halt testing. This is of very limited value in the sense of the design's firm. It becomes very difficult to make the argument to make changes when that is the entire point of halt. The objective of halt is to yield design input. So the design is now at a point in the program where there's a lot of resistance. You have to show tremendous value or risk to drive a design change. Now, you will drive changes, but to skip the validation testing again later on, there's great risk. Not only do you not know how much you've improved it, you don't know if you've introduced something else. So here's this very powerful tool that yields tremendous return on investment. It can be done very quickly in its individual segments, but we're not getting the maximum benefit from it simply because of the environment and how it's being used in the program. Another, accelerated life testing. So important, so critical. Because with accelerated life testing, what we're hoping to do is to characterize a fundamental design characteristic, not just reliability, but design characteristic of when a wear-out behavior is going to occur. Now, because it's a design characteristic, it probably is going to happen relatively unified across the entire population. So a premature wear out for what's being advertised as full use life is devastating. So with accelerated life tests, which even though they're compressed can take time, what we're looking to do is characterize the wear out behavior, typically a normal type distribution, and we want to ensure that only a small part of that tail crosses over into the use life and contributing to the failure mode. So to do this, you have to run all your test units to full failure. You can't stop your testing when you've demonstrated its use life. If that turned out to be the point that the nominal design occurred, 50% of your units would fail within your designated use life. So we need to find out how far out that distribution mean is and how tight that standard deviation is. So quite often, the accelerated life testing happens so late that at best, you're staying a little bit ahead of the customer's experience and hopefully can do a recall if you find out something is immature. That is of tremendous expense compared to having indicators within the program. In so many cases in hindsight, it would have been worthwhile to extend product release and have had that information in comparison to having to do a recall. Reliability growth. The objective of reliability growth is to systematically measure and improve reliability during the product development process. This is where we find the input for really important project decisions, because we have established a reliability goal and we are measuring if the product appears to be capable of achieving that goal. We're usually demonstrating this in statistical confidence of the goal. So in doing this, we are observing failures and making corrections and improvements in the process, because that's the other part, is having a consistent root cause analysis methodology. Now, so we can project what we call the virtual MTBF, where these issues we believe we've solved, have we fixed them? But what is critical is a validation phase where you actually show that you have. I mean, this is in alignment with key project management decisions about should we go forward? Do we have technical risk under control? And this validation phase so often is eliminated because there's a sense of confidence that, oh, we saw these issues and we fixed it and we know what we're doing. And without the validation phase being done in the program, what you're effectively doing is handing the validation phase to the customer. And they hate doing that for you. You're not paying them, and they don't like the job, and they're not good at it. So, in a very high percentage of reliability growth programs, you will see this pushed out by the pressures of schedule and budget. And again, that's the culture and the environment that these tools are being applied. So, something interesting I've observed with testing is the difference in concept between test to pass and test to learn. And these don't sound very different, but they are of great difference. Testing to pass means that you're taking a test, there is a goal, and your objective is to pass the test. This is what you do in school, right? You want your best moment to show. You study very hard, you don't care if you forget afterwards, but you're looking for your best performance. Test to learn is I am looking to measure, observe for the point of improvements from the test results. So these are very different. And I see a lot of programs that start off with the test to learn mindset, but quickly become the test to pass mindset, because nobody wants to be the one slowing down the program, that you want to pass your tests. The engineers have great interest in making sure that their features and technology are not the ones slowing it down. So how important is that mindset? It sounds kind of small, right? Not too big of a difference. How about this? I'll put you guys in the hot seat. What if you were in charge of developing an entirely new type of airplane? Now, that's great, and you have a program that you're accountable for, you have a budget, you have a schedule. What happens if your family is going to be the first passengers in that plane? Are you running programs test to pass or test to learn? Are you want to see it pass the test, or do you want to learn about every possible failure mode that could occur so you can address it? So think about that for a moment when you're doing testing programs. Are the project leaders testing to pass or testing to learn? Would they put their family in the airplane that that program created? So, I'm going to be going into some tools and techniques that I've developed and implemented and seen success with in programs. And I'm going to be talking about and sharing some scenarios that are probably very common with you about the type of negotiations that happen. And these tools and techniques you're going to be able to take next week when you go back to work and begin to implement them. They are methodologies that help shape the environment the way the environment shapes the program. So I've also, in this you'll see, made markers that at the bottom of the slides, because it's shared responsibility. We can't just put this on the leaders of the organization. So if you see a blue marker and you're a manager or a leader, this is an opportunity for something you can implement right away to help your programs. If you're a reliability engineer or reliability leader, the yellow marker indicates a tool or technique that right away you can implement and begin to benefit the programs. So let's start talking about both sides of the negotiation table. So much of it is negotiation. We start off in agreements of how a program is going to work, how things are budgeted and be allocated, and then there become these points of intense negotiation. On one side, you might have somebody who's interested in warranty objectives, somebody else who's very interested in reliability objectives is sitting there next to them. Time to market and developing new technology may be on the other side of the table, and they're competing for resource. These negotiations happen, and they, of course, get triggered when there's pressure. Now, you might have a discussion like, what is the true time to market if we have a field recovery phase? That's a good point for reliability to bring up. You're pushing for time to market, but have you really counted, if you look historically, all the other time we spend recovering once released? But there's a good argument, too, with the time to market people saying, well, what freeze, the design freeze, and maybe a tooling freeze in the program. So if you think about it, the idea there is, with freeze is, it's a put your pencils down, right? Remember when you're in tests, standardized tests, and they tell you, put your pencils down, you're done. That's it, not negotiable. This is not the right type of tool for this application, because that's never the way it actually goes. When you see a tool or method applied and it never actually is done that way, there's always negotiations when you come to design freeze. When you see that, it's not right. Something needs to be changed. So what I've found is, if you look at the way the behavior really occurs, there's a period beforehand where you have a chill, right? Effectively a slow firming up of what is flexible or can be negotiated. So I think creating a relationship between us and acknowledging that if in a reliability test, you are finding risks to the product that's being developed, what really happens in those hallway discussions is how much of a risk versus how much does it affect the program. And as you get closer to the freeze points, it gets firmer and firmer. It gets harder and harder to decide to make that change. You have to have greater and greater risk. So what occurs is this very clear understanding and awareness of this, with the reliability team having these inputs going back, as opposed to other people standing strong to simply protect those freeze points. So in creating that relationship of risk versus program impact and trying to find a way to even make it quantitative, we can, instead of freezes, have an understanding of the changes in firmness in the program and if things can be affected. And I'll talk a little bit more about that later on. Another method that I wanted to talk about is based on the idea that when there's program needs, that's when we select a tool, right? We have a need for something, we select a tool. In this case, we have a decision we have to make at alpha, we need information, let's get a tool. Now, if that information comes much later, it's of much less value if it's past that decision point that originally was the intent. And this happens over and over again. A methodology that I propose, and I've seen some good response with, is I call anchoring. And the reason why I call it anchoring is an anchor is a marker. It holds something in place, and it takes effort to relocate. It's not that you can't relocate it, it's that you have to consciously relocate it. So how does this anchoring methodology work? Very simple. There's 2 points, there's 2 anchors. There's the intent, and there's the delivery anchor. So in this case, if you had a need, such as you need design robustness input, you would select a tool like halt testing. And your need is at the design freeze for this information, with that firming chilling coming up to it is with regard to if it can be implemented. But it's obviously of low value when it's completed out there. So that is, as I point out, one area of concern that we're looking to mitigate against. But there's another as well. What if it is on time, but there's an iteration, right? You complete a test, quite often you want to rerun it because you've discovered something and you changed something. So now that information you needed, the really helpful information is, again, it's late. This wasn't accounted for. The method is simple. With the intent anchor, the way you create it is you attach it to quantitative risk. So something like a DFMEA, that is where you find the origins of when tools are initiated, right? You find high risk, you say we need to know this piece of information, and the action coming out of the DFMEA is very likely to be that test. So many of them go back to that. So by maintaining that connection and keeping it in the program as something that's highlighted, now there's an understanding of what the consequence is if there's an attempt to renegotiate when that test will start. Because now the whole team, it's not just the reliability engineer, the whole team has initiated that. Because the whole team was at the DFMEA. It's their action item from their analysis is the reason why the tool is done. And that connection is maintained. That's an entirely different discussion to have with the team when there's compression from cost or schedule. So intent. It's a simple word, but it's a very important word. So how do you create the delivery anchor? Well, the delivery anchor simply looks to the intent anchor, the intent. So there was either need to help a business decision or design input, and we have to look at the delivery. Is the delivery going to match that original need? Now, this isn't just important in the sense of negotiating why you have to do the test. As the reliability engineer, you see the yellow marker there, you're also responsible for saying the way this test is going to be implemented, we're not going to get very good value out of it. There's no way we can complete it by this date. And to suggest canceling it. As the reliability engineer, cancel it. Because you want to maintain the perception of high value in these different tools that are executed and always be able to give and take. There are tools that are going to be pressure that you want to maintain, and you could suggest taking resource from here and placing it on the other side. So risk in our environment, right? We've talked a lot about risk. You talk about DFMEAs, we understand how risk is worked with there. So we should be using risk assessment for program decisions, not just product decisions. It's a good technique to quantitatively look at risk that previously was kind of hypothetically and evaluated from individual positions, and putting numbers to it and then sorting it by that and having the entire program be in synchronicity. Why don't we do this with program decisions the same way we do it with product decisions? So at DFMEA, the team comes together And they, through having set definitions for scoring versus effects to the severity, the likelihood of occurrence, the detectability of an issue with the design, they are able to prioritize where they should put resource. A method that I would like to propose is what's called a process risk effects analysis. So you obviously can see the parallel and inspiration from a design failure modes effects analysis. So in this, the team comes together in a similar format. They look at the impact to reliability and the impact to program goals. This is what we're going to be looking to balance. We need to make decisions when there's an issue for a program. Which do we do? Where's the greater risk? To the product or to the program? So warranty and sales are 2 points that I often like to put a quantitative scale to, the way we do for severity, occurrence, or detectability for a design. And time to market and features are the other 2. And you can see the time to market and features are correlated to the program, and the warranty and sales are correlated to the impact to the reliability of the design. This is an example, a set of definitions, the way you would do severity, occurrence, and detectability, a 1 through 5 scale. So for warranty, you can see here, 1 might be a low warranty cost and a highly reliable product, so it's a low risk. 5, loss of future sales and a high dollar warranty cost is the effect of not addressing this issue. With sales, you can put a range that's appropriate with regard to what's considered a high sales loss versus a low. And then features, obviously 1 is you have all planned features are going to be completed in time and be mature. And then 5, you're going to not have this for some of the key fundamental features. And time to market, 1's on time, 5 is late. And the actual numbers only need to be agreed upon in advance. But of course, for different types of products and programs, the actual range will be different. So how do we use these numbers? Very simple. We're looking to see, after creating these measurements on these risk factors, where are we being driven to mitigate the most risk to the program, not the product? So a simple equation is you have a balance factor, which equals the warranty times the sales minus the time to market times the feature score. So if the B is negative, the freeze should be held. You shouldn't negotiate or change the way the program structure is going to be to mitigate that risk. It turns out the impact to the program is much greater. And if B is positive, the freeze should be flexible. The risk to the product is so high that it's very likely that the final outcome for the product and the program, where you might have things like recovery phases later, should be mitigated and given priority. So a simple example would be, we, at a point in the program, realize we had an issue. We do the PREA process. We give the warranty a score of 3, sales a score of 4, time to market 1, features 3. We end up with a positive value of 9. So with this positive value of 9, we realize quite strongly the freeze gate should be flexible. We should allocate the flexibility of schedule or cost to improving the risk we've identified with the product. So again, instead of us all sitting on the opposite sides of that table as I described, we're now together in assessing risk and agreeing upon quantitative values that will feed into a higher level decision together. And at the end, you can't really continue to debate it if you've agreed upon that process in advance and you've already had your input. But you're not on opposite sides of the negotiating table. You're functioning as a team, holding the goals that the company has to hold through, because you're now accountable, taking accountability for the full program the way the company does. So with this, you end up as a team keeping the balance. So reliability culture. It's creating the surroundings for a successful development of reliable products. Thank you very much.